Okay, folks, getting into this next learning goal, 10.9, be familiar with physisorption, chemisorption, and surface chemistry. So surface chemistry is kind of an umbrella term for people who look at chemistry occurring at molecular interfaces. And there's a wide application for this, ranging from environmental atmospheric chemistry, like what I do, to catalysis. So we're going to focus on surface chemistry as it pertains to catalysis and kinetics. But right, we should recognize that this type of view, this what I often call a molecular view of a surface, can be applied widely, even into biochemistry, right? The surface of the cell liner, for example. So we start with the terrace step kink model, which basically is a simple model that says if we zoom in on the surface of a material, and we'll call this material the adsorbent, okay, and typically that is a solid. If we zoom in at the molecular scale, we will see defects, okay? So those defects are where the unit cell at a certain point has to be cut off, and it can often be difficult to cut that off in an easy way. So we'll often see those steps and defects occur along unit cell lines. And when we see our atom here, or sometimes referred to as the adsorbate, those typically have a strong affinity for these defects, right? So if you imagine placing an atom like right next to this step, as opposed to out in the middle of this terrace, it's going to be able to experience intermolecular forces from both the terrace and the step. Whereas just on this open terrace, it might not bind as strongly. So we quantify how much adsorbate has adsorbed by the number of monolayers. So that is a capital theta, which by definition is the number of adsorption sites occupied. So that's referring to how many adsorbate molecules have condensed versus the number of adsorption sites available. And so that's related to the adsorbent. So how many sites are available from the adsorbent. So, and we can divide this type of adsorption into two main classes, physisorption or chemisorption. And those are often really important elementary steps observed in heterogeneous catalysis. So for example, in this reaction here, elementary step of carbon monoxide reacting with O2 over a platinum catalyst to form CO2, this occurs in this heterogeneous catalysis way. So a CO molecule has to land on this surface in order for this reaction to be catalyzed in this heterogeneous way. So getting into those differences between physisorption and chemisorption. So physisorption is typically through the van der Waals force. So the interactions can have very long range, but are typically very weak. On the other hand, chemisorption occurs through chemical bond formation. So we make a new covalent bond between the adsorbate and the adsorbent. And the interactions are usually very strong and are surface dependent, right? So if we look at these physisorptions and their enthalpy of adsorptions right here, so you can see they're all negative, so it is beneficial for these to land on a surface and adsorb. But you'll notice there's no indication as to what the surface is, and the values are on the smaller side. If we now look at typical enthalpies of chemisorption, for one, we can see that it is substrate dependent, substrate or adsorbent. We could use either term. But because this is forming a new chemical bond, right, the chemical identity of the adsorbent matters, right? So if we look at the adsorption of ethene on various surfaces, you can see there's quite a difference ranging from chromium to iron to nickel, okay? So now the way in which we quantify adsorption onto surfaces is fascinating to me. So there's several techniques that are considered surface sensitive techniques that are used. The main one that I'm going to highlight this semester is known as the DRIFS technique. So that stands for diffuse reflectance infrared Fourier transform spectroscopy. So this is just a very fancy sample holder that's placed in a commercial FTIR spectrometer. So this is not like any special type of spectroscopy. It's just regular old FTIR spectroscopy. However, it is a very special type of sample holder. So in a DRIFS cell, we will place a solid sample of interest. So sample, and I'll note that that is our substrate or our adsorbent, okay? And that will be located right here in our sample holder. And notably, this technique is used for gas to solid adsorption, so gas to solid. We could also consider the liquid to solid adsorption in this same type of heterogeneous catalysis in physisorption or chemisorption. And these DRIFS cells often have complicated gas flow manifolds where our adsorbate now in the gas phase can flow over the surface of our sample and can stick and land. What's really cool then about the way this technique works is it takes that IR beam from the FTIR spectrometer, it focuses it on the surface of the sample, and through careful backgrounding and ratioing, we can ratio out the gas phase spectrum and only see the spectrum of the surface. And it is important to note that this will pick up only those surface molecules, as we don't expect the IR beam to penetrate too deeply into the sample. So kind of back to this example I was talking about, the oxidation of carbon monoxide to form carbon dioxide. So it's known that carbon monoxide will chemisorb to the platinum surface. We'll put a PT right there. And the way that we get evidence that that has adsorbed is by looking at the spectra. So for example, because this is chemisorption, some of the electron density in this molecule will end up becoming delocalized. So it will flow into the metal. As a result, that pulls out electron density from that bond. And the result is it changes the vibrational frequency. So for example, if we were to look at a gas phase spectra, so I'll say gas phase carbon monoxide, and I'll draw this as like percent transmittance, we'd see a peak corresponding to that. Technically, we'd get a doublet, and I don't want to get into too much detail about that for now. And this would occur around the 2170 wave number mark for the gas phase. However, if we ratioed out that gas phase spectrum, and now we are looking at adsorbed CO, so I'm going to write AD in the phase to note that we're not really calling it a solid, we're not really calling it a liquid, we're just saying it's now been adsorbed. So we would see that peak shifting to lower wave numbers relative to the gas phase. Okay, so shift can be on the order of 100 to 200 wave number lower. And that is because this electron density has been removed from the bond between the carbon and oxygen centers and into this new chemisorbed covalent bond. And that makes this vibrate at a smaller frequency, right? So we see it shift into lower frequencies. And that would give us that spectroscopic evidence that adsorption has taken place. From there, what's really cool with this technique, you could continue to monitor the spectra as you then pump O2 over the surface, and you could actually monitor this chemical transformation in real time using this technique, which is really cool. Okay, so that's enough for this learning goal. We'll continue along with this in the next one. I'll see you then.